So hi all, I'm a recently joined postdoc here. So I'll be talking on the research which I did few months ago. And I'll talk on what can make a neutron star get converted into a quark star. And if a neutron star becomes a quark star, what can be the observational signatures? So in our universe, we have seen different compact stars. The compact stars are the endpoints of stellar evolution. We have white dwarf, we have neutron star and black hole. And these stars are called as compact stars because a huge amount of mass is contained in a very small radius. For example, the mass of sun, which is a main sequence star, is 1 solar mass and its radius is 7 into 10 power 5 kilometer. And the mass of Betelgeuse is 10 solar mass. It's a supergiant star and its radius is 10 power 9 kilometer. But the mass and radius of a white dwarf, neutron star and black hole will be like much smaller than like the radius of these stars are much smaller than this main sequence star and the supergiant star. So this white dwarf, neutron star and black holes are called as the compact star. There is another interesting class of compact star called as the quark star. These quark stars are theoretically possible, but observationally we have not been able to yet identify them. And there's an interesting scenario in which a quark star can get formed, and that scenario is that a neutron star can get converted into a quark star, and that can happen when the quarks which are present inside the neutrons and protons get deconfined. We will have a sea of up and down quarks, and that can give rise to a quark star. And when a neutron star becomes quark star, there is huge amount of energy liberated, and that can get converted in the form of gravitational waves and some EM observation. And by observing these emissions, we can conclude that a quark star got formed and a quark star exists in our universe. And the main line of this research is important because we have seen white dwarfs, neutron star and black hole, and we have theoretically predicted them, we have observed them, but quark star is still awaits any observation yet. So what is the motivation for the existence of quark star is from this that I'll tell in this slide. So this is the mass sequence for a neutron star. In the y-axis we have masses, and in the x-axis we have the central density. So we see that a neutron star of 1 solar mass has a density of like 5 into 10 power 14 gram per centimeter cube. A neutron star which is of 2 solar mass has a density of 10 power 15 gram per centimeter cube. And this is the mass versus radius diagram. And here we can see that in 1 solar mass neutron star has a radius of 13 kilometer. A 2 solar mass neutron star has a radius of around 14 kilometer. So 2 times the mass of sun is just confined in very small radius of 15 kilometers. That is from here to the city center, we have 2 times the mass of sun present in just 15 kilometers. That dense the neutron star is, and the densities are 10 power 14 to 10 power 15 gram per centimeter cube. In our periodic table, we have atomic nuclei of smaller atoms and even of bigger atoms. And the average nuclear saturation density that we see in the terrestrial nuclear matter is 2.5 into 10 power 14 gram per centimeter cube. And the neutron star interior densities at the center is like 4 times to 6 times of this particular value. At these high densities, there is possibility that the nuclear matter may not be existing, and it could be quark matter present at such densities. Also, there in the seminal work done by Witten in 1984, he suggested that at densities few times the nuclear saturation density, the nuclear matter is no longer the stable ground state. The 3-flavor quark matter consisting of up, down, and strange quark is likely to be the ground state at such densities. If 3-flavor quark matter is the actual ground state, then in some dense neutron star, what can happen is that the matter can get converted into quark matter, and a neutron star can make its journey to a quark star. A neutron star's journey to quark star is likely to be happening by 2-step process. In the first step, there will be deconfinement. All the protons and neutrons which are present, from that the quarks will come out, and we will have a sea of up and down quarks. After the up and down quark has come out, since this is not the stable ground state, it has to reach to up, down, and strange quark. There will be weak decay process. And after the weak decay, we will have an up, down, and strange quark. And once this gets formed, a neutron star becomes a stable 3-flavor quark star. So when a star makes journey from this step to this step, we will get a quark star. But what can make a neutron star which is born as a neutron star suddenly go into this journey to become a quark star? And what can make this trigger happen is what I will tell. So these kind of things can happen in the neutron star at its birth. When a neutron star is getting formed after supernova core collapse explosion, when the inner iron core is getting compressed, at that time itself the density may rise above few times the nuclear saturation density, and the quark matter can appear and a quark star can get formed. Or it can happen during binary neutron star merger, in which 2 neutron stars, when they come together and they collide, and a hypermassive neutron star is formed. And in this hypermassive neutron star, the densities may be high enough that quark matter can start appearing. It can happen in, it can also can also happen with the isolated neutron star. That is a neutron star which is formed as a neutron star in its lifetime. If it accretes matter from its nearby companion in binary, when the mass comes and gets accreted, its density may rise, and a neutron star can make its journey to a quark star. Also, there is another interesting scenario. A neutron star which is formed, it has magnetic field, and it slows down over the time due to magnetic energy, electromagnetic radiation emission. And when it slows down due to magnetic braking, and that spin down can also lead to it becoming a quark star. And I have studied this spin down scenario, which I will show in this next slide. Also, there is some uncertainties about the nature of the quark hadron interface. The uncertainty is that when the first time the quark matter appears inside, whether that quark matter and the nuclear matter will be like touching each other smoothly, or whether there will be density discontinuity. For example, in this we can see that this is the pressure versus energy density plot, and here you will see that the pressure is, this is the nuclear matter, this is the quark matter, and there's a density jump here, and this is called as the Maxwell construction. This happens if the surface tension is quite high between the nuclear and the quark matter, such that there is a density jump at their interface, and this is called as the Gibbs construction. And in this, there is a nuclear matter, quark matter at the high density, and in between there is a mixed phase in which the nuclear matter and quark matter will be in the mixed form, and that happens if the surface tension is 0. So the nature of the equation of state is uncertain of the interface. So I have considered two types of equation of states, one with the Maxwell construction and another with the Gibbs construction. The Maxwell construction equation of state has some density discontinuity. The quark matter, this Gibbs construction don't have any discontinuity. What there exists a mixed phase between the hadronic matter and the quark matter. And this different equation of state shows that here there is a transition from nuclear matter to quark matter. In this equation of state, there's a transition here. And in this equation, there's a transition at very high value. So this is the study which I have done. So what I have taken is that I have taken the neutron star at birth, and then I tried to see when it slows down over its life, what can happen to it. So this particular gray curve is the mass versus central density curve at the Keplerian frequency. When the neutron stars are born, they are very rapidly rotating, and it is good to assume that they are at the Keplerian frequency. So the neutron stars lie at this gray curve. So when this blue curve is when they are not rotating at all. And so in the intermediate curves, the yellow one and the green one and the light blue one corresponds to when they are like slowly rotating. So neutron star, when it is born, it will lie at the Keplerian curve, and then it will jump from that to the slow rotation curves. For example, in neutron star, which is at 1.4 solar mass, it is here. This blue line here represents the phase transition line, by crossing which the neutron star can become a quark star. So 1.4 solar mass neutron star at the birth is on the left of this line. It's a neutron star. When it slows down at some particular frequency, it will cross this line, and then it will become a quark star. A 1.2 solar mass neutron star, though it slows down, it jumps the curves, but it never crosses this line, so it always remains a neutron star. There are some neutron stars at the birth itself at Keplerian frequency. They are on the right side of this line, and they have some quark matter. And when they slow down, the density increases, central density from 7.5 into 10 power 14 to 12.36 into 10 power 14. They jump from the Keplerian curve to slow rotation curve. The density increases. And there are some neutron stars which are at this top. So when they slow down, they jump the curve from Keplerian curve to slow rotation, but they don't find any stable counterpart, and these neutron stars eventually collapse to black hole. So there are some neutron stars which remain neutron stars, some from neutron star become quark star, some are born as neutron quark star, and their quark core grows because the density is increasing. Some are born as quark star, but when they slow down, they don't find any stable counterpart because they're so massive that when they slow down, the centrifugal force is not there to balance the mass, and they become black hole. So these are the scenarios which comes out in my analysis, and that is shown in this particular curve also. So this is for Keplerian frequency, this is for slow rotation frequency. So the smaller ones remain as neutron star. The bigger ones become hybrid star, where they attain quark matter cores, and much massive ones, when they slow down, they don't have a stable counterpart, and they become a black hole. So in this curve, I show this is called as the quark core mass fraction, mass of quark core divided by the mass of star. So we can see that there is a neutron star of 1.8 solar mass. It has a quark core at the birth at high rotation. When it slows down, the rotation frequency decreases, and we see that the quark core content is growing. There is a neutron star of 1.4 solar mass, the blue curve. Its quark content is 0 at the birth at high frequencies. As it slows down, it jumps from 1000 Hz to 800 Hz to 600 Hz. And somewhere after crossing 600 Hz, the quark matter starts appearing inside it, and then it keeps growing. So this is the thing, and this is the radius of the quark core. Initially, we see that for most of the neutrons, the radius of the quark core is 0. But when they slow down, in 1.4 solar mass, neutrons are around 600 Hz, they attain quark core, and the radius of the quark core becomes 3 km when they arrive at 200 Hz. For a 1.7 solar mass neutron star, which is this yellow curve, we see that it didn't have any quark core, but quark core
2
appears,
minutes left.
And then we see that it keeps growing. So when this quark matter is appearing inside the neutron star, how can we observe it? The one way to observe it by seeing the change in the breaking index. So this is the breaking index formula, and it depends upon the moment of inertia and the moment of inertia's derivative. So in this plot, we can see that the moment of inertia of neutron star is here, and it becomes quark star. The moment of inertia attains some flatness, and by observing this flatness, when we substitute this particular value here, we will see that there is an anomalous change in the breaking index. For most of the pulsars, the theoretical breaking index is equal to 3 for magnetic braking, and there will be some anomalous change in the breaking index suddenly because of quark matter appearing. And also there is another one particular way which we can observe this gravitational wave is that from gravitational waves. So this is the gravitational wave formula due to oscillation modes, where h0 is the amplitude. It depends upon the energy emitted, oscillation mode's frequency, and the damping time. This is the frequency omega naught. This is the damping time of the oscillation mode. For F mode, the frequency and the oscillation, the damping time can be obtained by these formulas. It depends upon the mass and the radius. So here is the F mode's evolution when there is only spin down, the black curve, when there is spin down plus phase transition, when quark matter appears. We can see that when phase transition happens, there is a deviation in this. So by substituting the energy emitted and the oscillation mode frequency at this particular point, when the first time the quark matter appears, I have estimated the gravitational wave. It looks like that. If we zoom in, we see that there is some things are there. So one more minute to conclude. So by observing, so there can be also another emission. As I told that the neutron star to quark star conversion happens by weak decay step. First, there's a deconfinement, there's a weak decay after that. The weak decay leads to some neutrino emission. The neutrinos, when they are emitted, they can give rise to short gamma ray burst. Also, since the quark star is a bit compact than the neutron star, the magnetic energy which is present in the atmosphere also can get converted into fast radio burst. So this looks like a multi-messenger conversion. We will have gravitational wave, we will have neutrino emission, we will have short gamma ray burst from the neutrinos. Also, we will be having some FRBs due to the magnetosphere energy which gets converted. So all these I calculated. So overall, since the equation of state is uncertain, the particular candidates, the quark star candidates or the black hole candidates which can become from neutron star, the mass ranges differ because since we don't know which is the exact equation of state which is followed in the nature. So I carried out the analysis with different equation of state. So this is at the birth stage, this is the mass range for neutron star. Birth stage is the mass range for quark star. At evolution stage, this is the quark core candidates mass ranges, and this is the mass ranges for black hole candidates. If neutron star is above 2.05 solar mass, when they slow down, they will become quark star. If a neutron star is 1.72 to 2.22, for this particular equation of state, they will become quark star when they slow down. So overall, to summarize, a neutron star which is born, when it slows down, it can attain a quark core. Some neutron stars may have already a quark core that will grow with time. Some neutron stars may have a quark core at birth, but they're so massive that when they slow down, they can become a black hole. So neutron star can become also a black hole, can also become a quark star in its lifetime. By observing the signals which come during the conversion, we can conclude that a quark star has formed in the universe. And these signals like the GWs, the neutrinos, GRB, FRBs, and the anomalous change in breaking index can help us identify the quark stars in our universe. So thank you.